You ever look at a massive bridge and wonder, how did they get both sides to meet perfectly in the middle? Or how does water in a canal flow exactly where it's supposed to? Well, it's not magic. It's this hidden science that builds our entire world straight and true. And today, we're going to pull back the curtain on the fundamentals of surveying.
So let's dive right in. How do we even begin to get from a plan on a piece of paper to a massive finished structure? Well, it all starts with solving a huge fundamental challenge that engineers and builders face every single day.
Right, here's the core of the problem. We live on a giant sphere. So what you think of as a straight line, say a laser beam, doesn't actually follow the ground. It just shoots straight off into space. And this isn't some small theoretical thing either. Get this, over just 1 mile, the Earth's surface drops by about 8 inches. So how do you build anything level when the very ground you're on is curving away from you? Well, that is where the meticulous art of surveying comes in. So surveying is the discipline that solves this very problem. It's all about figuring out exactly where things are in 3D space with unbelievable precision. And for our purposes today, we're going to zoom in on one of its most essential techniques. It's called leveling. Okay, so what exactly is leveling? Simply put, it's the part of surveying that's all about measuring height, or what they call elevation. And to really get it, we need to nail down a few key ideas first.
This image right here, this explains the whole puzzle perfectly. See that level line? It's curved. It follows the curve of the Earth. Just think about the surface of a big, calm lake. That's a level line. But the horizontal line, that's the perfectly straight line of sight coming out of a surveyor's instrument. The surveyor's entire job really is to precisely measure the gap between these two lines. Now, if you're going to measure height, you need a starting point, right? A universal zero. For the whole planet, that starting point is called the datum, and it's usually mean sea level. And that's not just a guess, it's the average height of the entire ocean calculated across every tide over a 19-year cycle. That's the level of precision we're talking about. Okay, but you can't exactly bring the ocean with you to a construction site in the middle of a continent. That's why surveyors use benchmarks. These are fixed, permanent points, like a little metal disc set in concrete that have a precisely known elevation. You can think of it like a save point in a video game. It gives you a reliable, trusted height that you can start measuring from, no matter where you are. All right, so we've got the concepts down, but what do they actually use to take these measurements? Let's take a look at the actual tools of the trade. Let's meet the two main characters in this whole operation. On the left, we've got the level. That's a super high-precision telescope. And on the right, that's the leveling staff, which is basically a giant, incredibly accurate folding ruler. It's the teamwork between these two tools that makes everything possible. Now, the level itself looks complicated, but it's really a marvel of single-minded engineering. It has one absolutely critical job: to create a perfectly horizontal line of sight. It's got a telescope to see through, a super sensitive bubble to make sure it's perfectly flat, and a sturdy tripod to keep it rock steady. Okay, let's put ourselves out in the field. How does this all come together? What does the surveyor actually do to take one of these readings? Well, it's a careful process that demands perfection every single time. So before they even think about taking a measurement, a surveyor has to do these 3 temporary adjustments. First, they set up the instrument. Then, they use these tiny little screws to get that bubble in the level tube dead center. That's what makes the instrument truly level. And finally, they focus the optics to get rid of something called parallax. That's just a fancy word for an optical trick where the crosshairs seem to move around if you shift your eye. Getting rid of it means what you see is exactly what you get. And this is the result of all that careful setup. This is the view through the eyepiece. You get this crystal clear shot of the leveling staff, and that horizontal crosshair lands right on a specific mark. It lets you take an incredibly precise reading. In this case, 1.753 meters. So one reading is just one number. That's great. But how do you turn a whole series of these numbers, taken from all different spots, into a useful map of the ground's ups and downs? That's the next crucial step. So let's walk through a real-world example. A surveyor has to map out a piece of land, so they take a bunch of readings. And since they can't see the whole area from one spot, they have to move the instrument several times. They start their work at a known benchmark with an elevation of 432.384 meters. They log all their readings in a table like this, using what's called the rise and fall method. The logic is actually really simple. Think of it like walking up and down a small hill.
By comparing two readings, they can calculate if the ground between them went up, that's a rise, or if it went down, a fall. Then they just add that rise or subtract that fall from the last known height. They just chain these simple calculations together, one after another, and build a precise elevation map of every single point they measure. And here's the beautiful part. Because this is all about precision, there's a neat, built-in check to make sure they got it right. The sum of all the rises, minus the sum of all the falls, has to equal the difference between their very first elevation and their very last one. If those numbers don't match up perfectly, you've made a mistake somewhere and you have to go back and find it. There is absolutely no room for error.
Okay, let's bring this all home. Why does this painstaking process of measuring and calculating actually matter? Well, it turns out it's fundamental to pretty much everything in the world around us.
Here's a really cool, practical problem that surveyors have to solve. The person looking through the instrument might be hundreds of feet away from the person holding the staff. On a busy, noisy construction site, how on earth do you communicate? You can't just shout. And the answer is just so brilliantly simple and low-tech. They use hand signals. And this isn't just basic waving. It's a whole precise language. A rapid arm movement might mean move the top of the staff to my left. Extending both arms down means that's it, establish the point. It's this silent, efficient dance of precision happening on job sites all over the world. So remember those questions from the very beginning? How do bridges meet perfectly? How does water flow exactly where it should? This is the answer. It's the hidden, careful work of surveyors applying these exact principles. This level of precision is what makes our modern world work. It ensures that roads drain, bridges connect, and our buildings stand strong on a foundation of absolute accuracy. Kind of makes you wonder, doesn't it? We've just peeked into the science of the level line, but what other invisible layers of data and measurement are all around us, quietly holding our complex world together? The next time you walk around, just look. You're right in the middle of them.